Okay, here we go, pre-calculus. It's been asked that I show a handful of these examples. You can see that the solutions are down there. I've selected 6 problems from your homework, and we're going to investigate each of those. Okay, so let's start off with number 7. The first thing with number 7 is realizing that the decimal 0.999 should really be written or considered as, we'll rewrite this, the limit as n approaches infinity. We should think of this as 999 over 1,000, and that's raised to the nth power. We then further expand this and realize, again, the limit still stays there, n approaches infinity, but this is 999 to the nth over 1,000 to the nth power. Now, once we've done this, we realize that the denominator is larger than the numerator. So the denominator will grow much, much larger. At that point, as n approaches infinity, we know that the limit is actually equal to 0. And again, the denominator is much, much larger than the numerator when the exponent goes to infinity. Hence, the limit itself will be equal to 0. Moving on to number 8. Now this one, there's a lot of different techniques to it. You may be able to tell, based upon what we talked about in class, that because the degree of the denominator right here is larger than the degree, any degree of the numerator, the denominator will grow much faster and the limit will be 0. Some students don't like that approach, so instead what you can do is you can divide every term in the entire polynomial by the highest degree of the denominator. So I'll rewrite this as the limit as n approaches infinity, but I'm going to rewrite these and divide everything by the highest degree. So I'm just copying right now. So 9, 9, 9, 9, 9, and then 3 more 9s, all over n cubed. Now what I do is I'm going through and I'm going to divide everything by the highest degree of the denominator, which is n cubed. So now our simplification is going to yield, and this is just purely exponent properties. I haven't actually evaluated the limit yet. I can look at the numerator, and this turns out to be 1 over n plus this number 9999999 over n cubed all over 1. So now I can evaluate the actual limit itself. The limit itself, again, 1 over infinity for this is that first term in the numerator tends to 0, plus that large number divided by infinity cubed still tends to 0, divided by 1. Therefore, our limit is still 0. Nothing has changed there. Number 18 is pretty much the same deal, except that they're trying to hamper us with some rational exponents. Again, one thing that I would look at on this particular problem is notice that the highest degree of the numerator is 5/2. That's 2.5 versus the highest degree of the denominator, which is only 2. So the numerator will grow much, much faster than the denominator, which explains to us why the limit itself is still positive infinity. Now you can still take and divide every term by the highest degree of the numerator, and everything will still work the same. I'll show you that right now. Again, same process as the one we just saw right above. So you could think of this as 5n to the 5/2 power over n squared minus 7n over n squared. And then the denominator we have n squared over n squared plus 10n over n squared. That entire chunk. Now again, we're going to apply our exponent properties. The limit hasn't actually been evaluated yet, and we are going to get something like this. So if you have 5n to the 2.5 over 2, that essentially leaves just n to the 1/2 power. So that's the square root of n. That's what is left behind. This one here is minus 7 over n. Here you have 1 in the denominator, and here you have 10 over n. Now let's take a look at these limits individually. So on a test or quiz, you may choose to not rewrite every single one of them. So here you go. The square root of n. Well, if n tends to infinity, then this term goes to infinity, because the square root of infinity is still infinity. 7 over infinity tends to 0. Your 1 is still left down there, and I erased my sign accidentally. That's plus 0. So you end up with infinity over 1, which is just infinity. And as you can see, that is the same value as what we have up over here. Our next problem is going to be number 20. Number 20 I've chosen because we can see that the limit is negative infinity. So there's a little bit more trickery going on with this particular problem. So let's use the tactic that we're going to divide by the highest degree of the denominator, which is n to the 1/2. So if we do that, we have the limit as n approaches positive infinity, and I end up with 5n over n to the 1/2 all over n to the 1/2 divided by n to the 1/2 minus 3 over n to the 1/2. Now, that pen's not quite as accurate as I wanted it. Let's take a look at this in our simplifications. The limit as n tends to infinity, we're going to be left with, in the numerator, negative 5. Again, this is using exponent properties, so it's n to the 1/2 power over, well, the first term is 1, and then it's minus 0 because 3, again, looking at this, 3 over n, the square root of infinity, that's going to tend to 0. So now if we evaluate the limit, essentially what we have is negative 5 times the square root of infinity, because again, n to the 1/2 is the square root of infinity. Square root of infinity is still infinity divided by 1. Now the 5 isn't that big a deal other than the fact that we have to realize that it's negative. So 5 times infinity is just infinity, but the negative sign creates our value that gives us our final answer that tells us that this is actually negative infinity. Now let's leave 21 for the last problem. Let's go down here and tackle 23. And I'm going to leave this to you, but I'm going to show you the setup. So the key to solving problems like this is to write it so that it's under one radical. So if we rewrite this, the limit as n approaches infinity, and I want you to think of it as the cube root of all that quantity. 8n squared minus 5n plus 1 over n squared plus 7 minus, plus 7n minus 3. So we're going to deal with the radicand, or the stuff that's underneath the radical sign here. Now you're going to go through and use that same tactic that you did. You're going to divide every term by n squared. And what you're going to find is that the inside simplifies down to, don't need the limit because we're going to evaluate it. It's going to simplify down because they're the same degree as the cube root of 8 over 1, which is really just the cube root of 8, which very clearly the cube root of 8 is 2. And that is where that 2 is coming from. So again, the key is to write it under one radical sign and then evaluate the limit on the radicand and then deal with the radical sign. Now our last one is what happens when a limit doesn't exist? What's truly happening here? Well, this one is very conceptual. What I would encourage you to do, and what we're going to first look at, is this first chunk here. What happens on that stuff that I just highlighted? I'm going to write this little chunk in purple. Well, if you consider -1 the quantity to the first, and then -1 the quantity to the second, and -1 quantity to the third, and then so forth, you'll know that this goes -1, then +1, then -1, and it's going to continue to alternate back and forth, all the way up to positive infinity. So by letting n tend to infinity, it doesn't make a number larger or smaller in magnitude. It simply changes the sign on the number 1. Now, once we know that, the second part of this equation that I just circled that is -1, if we then take that value and subtract 1 on each case, then we know -1 minus 1 gives us the value -2, and then it goes to 0, and then it goes to -2, and then it goes to 0, and then it goes to -2, and this pattern is going to continue. So notice it's a pattern. We didn't use some algebraic step. We just investigated the scenario. Now, If you were to think graphically of what's happening here, if I consider this to be x equals 0, let's say 2 is somewhere up here, essentially as I'm plotting points, excuse me, I guess it's negative 2, not positive 2. As I'm plotting points, when n was 1, I ended up with negative 2, so it'd be somewhere around here. And then it jumps up to here, and then back down to here, and then up to here, and then down to here, and so forth, and it continues this pattern. The values do not converge towards a particular value. It just oscillates back and forth. That's why the limit does not exist, is because it doesn't approach some particular number as n approaches infinity. No matter how far you get out here to the right, you're not going to get a particular output. It's going to continue to give you two different values, negative 2 and 0. I hope that this information helps. Again, if you need additional help, don't hesitate to stop by during my office hours or utilize the Math Center. This is an important topic that shows up on the test, and it's an easy one to fix.